Hello, chemistry students. I'm going to use this time to review over Chapter 5, which is on electrons and atoms. To review, the test is going to be worth 48 points. We're going to have 6 multiple choice questions. There'll be 2 word problems that involve these 2 equations. And so remember, I will give you guys these equations over here so you can use these for tomorrow's test. Then we'll also have 1 problem that involves an orbital diagram. This is the one that involves the boxes and arrows. We will also have 4 ground state electron configuration problems, 3 of the noble gas configuration problems. We'll have 5 valence electron problems, which I'll talk about here toward the end. And then there'll be 3 matching problems. And so they'll be based upon the Aufbau principle, the Pauli exclusion principle, and Hund's rule. And so what you'll need for this test, you'll need, of course, a pen or a pencil. You'll need a calculator. And very, very important, you do need that copy of the periodic table that I gave you. And so make sure that you do have that. That'll make this test a lot easier. All right. And so with that being said, we're going to go ahead then and look at a couple of these word problems. So these are the word problems. All right, let me go ahead. I will write the question on the board, and then we'll go ahead and then we will answer it. So here's the question. So let me just adjust this just a little. Sorry. All right, so here's the question. What is the wavelength of EM radiation with a frequency of 5 times 10 to the 12 hertz? All right. Oops. So here's the question. What is the wavelength of EM radiation that the frequency of 5 times 10 to the 12 hertz? And so if we look over here at the board, we look at our 2 equations. And so notice that this equation involves both wavelength and frequency. So we're going to use this first equation in order to solve for the wavelength. And so notice we can rewrite this equation by bringing the frequency over to the other side. So we have to divide both sides by V. And so what we can say then is that the wavelength is equal to the C over V. Remember that C is the speed of light. That's a constant that will never ever change. So that's going to be 3 times 10 to the 8 meters per second. On the bottom goes our frequency, which we're told is 5 times 10 to the 12 hertz. And so to solve this problem, we take 3 times 10 to the 8 meters per second, and we divide by 5 times 10 to the 12. So let's go ahead, and we'll do that on my calculator. Remember to do scientific notation. This E button here is going to be your times 10 to the. So to type this in, it's going to be 3, hit the double E button, 8, divided by 5, the double E button, 12. And so when you do that, and so if you use the scientific notation for this, you'll see that you end up getting 6 times 10 to the 5 meters. And so this becomes 6 times 10 to the minus 5 meters. And so there's the answer. All right, and so hopefully that makes sense. Let's look at another type of problem. And so I'll go ahead and put that one up on the board as well. And so this problem, we're going to go ahead and we're going to answer what is the energy of a photon of red light that has a frequency of 4.5 times 10 to the 14 hertz. So let me go ahead and repeat the question. So our question here, what is the energy of a photon of red light that has a frequency of 4.5 times 10 to the 14 hertz? Notice in this problem, we're looking for energy, and so we're going to be using this equation. So E equals hv, and so E is for energy, the h here is for Planck's constant, which I have to provide for you, and then remember V again is still for frequency. All right, and so all we have to do then is just simply plug in what we're told and then solve for the answer. And so we can say that E equals, we have Planck's constant, which again I'll give you, this is going to be 6.63 times 10 to the minus 34 joule seconds. We multiply this number by what we're given, so this is going to be 4.5 times 10 to the 14 hertz. And so again, we're going to put this in our calculator. And so when we do that, we're going to take 6.63 E negative 34 times 4.5 E 14. And so we're going to end up with something roughly around 3 times 10 to the negative 19 joules. So this is going to be 3 times 10 to the minus 19 joules. And so we've now calculated the energy for this photon of red light. So the answer here is 3 times 10 to the minus 19 joules. And so remember, for the test, please show your work, and then when you get your answer, make sure it has the unit and then circle or box it in. All right, so that's how we do those word problems. Next, let's look to see how we do another type of orbital diagram. All right. Let's say, for instance, we want to do the orbital diagram for the element carbon. And so carbon, as you guys know, is essential for life. And in fact, there's a whole branch of chemistry called organic chemistry that's devoted to the chemistry of carbon. So let's go look for the orbital diagram of carbon. And so I'm going to make sure that I have my periodic table ready, because this will definitely help me out. So carbon, we look for carbon on the periodic table, and we note that carbon has an atomic number of 6. And so because this is a neutral atom, we also know that carbon is going to have 6 electrons as well. So the electron count here is 6. What this means is that when we do the box and arrow thing, we have to have a total of 6 arrows in order for this to work. All right, and so what we're going to do, we look for the lowest energy level, which is always going to be 1s. And so that's going to be just one box, because there's only one shape for the s. So we have 1s. So here's our 1s. Next, we have to go up to the second level. And so notice the second level, then we have 2s. And so again, we're going to use just one box, because remember again that the s orbitals only have one shape and therefore only have one box. Notice we're still in the second energy level. Notice we have to go over to the right, and so we have now 2p. And so if you guys remember, there are 3 shapes for the p orbital, and therefore there's going to have to be 3 boxes for the 2p orbital as well. So 1, 2, 3. All right. So these represent the orbitals for carbon. So we have 1s, which is one box, 2s, which is another box, and then remember 2p, because it's p, is going to have 3 boxes. All right. Remember again that for carbon, the electron count here is 6. And so we're going to start filling up the boxes with the arrows. We're going to go ahead and put an electron here pointing up. We'll put an electron here pointing down. We'll put another electron pointing up here, another electron pointing down here. Notice now we've filled in 4 electrons, and so 6 minus 4 is 2. And so we have to be careful, because we have to remember Hund's rule. And so remember, Hund's rule says that electrons don't pair up until they absolutely have to. So notice we have 3 empty boxes and we have 2 electrons. And so what we're going to do, we're going to put an up arrow here. We're also going to put an up arrow here as well. And so notice now we have 1, 2, 3, 4, 5, 6. And if you notice, you have a total of 2 unpaired electrons. So we have 2 unpaired electrons. All right, and so this would be how you would do the orbital diagram for carbon. So you get the number of electrons, you look at your periodic table to then look for the orbital boxes, then you fill up the orbitals with up and down arrows, remembering Hund's rule because these have to be pointing up, and so before you have them pair up. And so notice then that there are 2 unpaired electrons. And so this is how you would do this problem. All right, let's go ahead and practice again doing both the ground state electron configuration and the noble gas bracketed configuration for the element tin. All right, so let's go ahead and we'll do that next. All right, so we're going to do both of these for the element of tin. So tin, and remember tin is not T or Ti on the periodic table. Tin is actually represented here by Sn. And so Sn, the Latin word for tin, is stannum. So that's why that has that abbreviation. And so we have stannum. And so notice that the number, the atomic number here is 50. And so that also tells us the number of electrons. So tin has a total of 50 electrons. All right, let us first go ahead and do the ground state electron configuration for tin, and then we'll do the same thing then using the noble gas configuration. All right, so our ground state configuration as always, we have to start with the lowest energy orbital, which is always going to be our 1s. And so we go and we start with 1s, 1, 2. So that takes us to helium. 1s2. All right. Next, we go up to the second level, and then we go 2s1, 2. Then we're still in the second energy level, and so now we have 2p, 1, 2, 3, 4, 5, 6. Next, we go up to the third energy level, and so we're back over here on the left, so we have 3s1, 2. Then we go to the right, because we're still in the third energy level, and so this becomes 3p, 1, 2, 3, 4, 5, 6. Next, we go up to the fourth energy level. And so the fourth energy level with S is going to be 4s1, 2. All right. Notice then, when we enter the d orbital here, even though we're in the fourth row, remember that the d starts with 3. So that's why that 3 is right there. So we have 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we're going to have, back up to the 4, so we're going to have 4p, 1, 2, 3, 4, 5, 6. Okay. Then we're going to go up to the fifth energy level. So we have the fifth. So this is going to be 5s1, 2. Then, remember, this is not the fifth one, but 4 for D. So 4D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so 4D10. And then finally, we're going to go to 5P1, 2. So we're going to stop there. So 5P2. All right, so notice the electron configuration for tin: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. And so we can double check to make this make sense, because what we can do is add up all these little numbers and they should add up to 50. So let's go ahead and count to make sure this is right. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 2 is 12 plus 12 plus 6 is 18. 18 plus 2 is 20. 20 plus 10 is 30. 30 plus 6 is 36. 36 and 2 is 38. 38 and 10 is 48. 48 and 2 is 50. So we do have the correct electron configuration for tin. All right, so that's the ground state configuration. We can also represent this using the shorthand method of the noble gas configuration. Again, we're going to look at our periodic table. Again, we're going to locate tin. We're going to look for the noble gas that comes before the element. And so remember, the noble gases are on the far right column. And so we're going to see that that element is going to be krypton. So we're going to go ahead, we'll put the symbol of krypton in square brackets. So for our noble gas, we'll put krypton in square brackets. And then we're going to continue along just like before. So now we're going to be in 5s2. And then we have 4d10. And then finally 5p12. And so this now represents the noble gas configuration for tin. We can also check this to make sure that it adds up to 50. Krypton has an atomic mass of 36, or a number of 36, so it also has 36 electrons. 36 plus 2 is 38. 38 and 10 is 48. 48 and 2 is 50. So this is the correct noble gas configuration for tin. Krypton in square brackets, 5s2, 4d10, 5p2. All right, so that's for that one. And so one more thing we'll go through, and so we're going to look at the number of valence electrons for given elements. And so again, if you use your periodic table, it's going to make this a whole lot easier. Notice that in the first column, you're going to only have one valence electron. So these elements in this column have one, the alkaline metals. The alkaline earth metals here are going to have 2 valence electrons. We skip over the transition metals. The boron family of elements here is going to have 3. The carbon family is going to have 4. Nitrogen family is going to have 5. The oxygen family is going to have 6 valence electrons. The halogens over here are going to have lucky number 7. And the noble gases over here on the far right are going to have a total of 8. And so given any of the elements in this part here or over here, using the periodic table, you should be able then to tell me the number of valence electrons for any of those elements. And so with that, I'm going to go ahead and end the review. I hope that this was helpful. I want to wish you all good luck, and I will see you, most of you, then tomorrow for the test. And I hope you guys have a good rest of your day.